Hello, welcome. This is lecture 2. In the last lecture, we discussed two vector operations, namely the vector addition and scalar multiplication. Means how to add two vectors and how to multiply a vector by a scalar. In this lecture, we're going to talk about products of vectors, how to multiply two vectors. We have two such products. Let's begin the discussion with a dot product. So if we have two vectors, A and B, with components as shown, then the dot product of the vectors A and B is denoted by the symbol A dot B and is defined by this definition. So to get the dot product of two vectors, one just need to multiply the corresponding components of each vector and then add. So we note here the result is just a number. It's not a vector. And for this reason, this is sometimes also called scalar product or inner product. This definition is given here for a three-dimensional vector. But this can be also defined for two-dimensional vectors and can easily be extended for the case of n-dimensional vectors. Let's see an example. We are given two vectors, A and B, whose components are shown. We need to compute the dot product of them. By following the definition, the dot product is simply 7. Now we'll discuss the dot products of the standard basis vectors, I, J, K. Since we know that the components of I are 1, 0, 0, so if we compute the dot product of I with itself, we get simply 1. So I dot I equals 1. In a similar fashion, we can also show that I dot j is 0 and the rest, j dot j is 1, k dot k is also 1, but j dot k and I dot k are zeros. So if we multiply standard basis vector to itself, we get 1. If we multiply two standard basis vectors to different standard basis vectors, we get 0. Let's see another example. We have two vectors A and B expressed in terms of the standard basis vectors. We want to compute the dot product. By following the rules of the dot product of standard basis vectors, we simply obtain A dot B is 8 plus 1 minus 9, which is equal to 0. So the dot product of these two vectors is equal to 0. Now we'll discuss various properties of dot product. If A, B, and C are vectors in a three-dimensional space, and C is some scalar, then the listed 5 properties hold true. For example, the first property says the dot product of the vector A with itself equals the square of the magnitude of A. And the property 2 says the dot product of the vectors A and B is equal to the dot product of the vectors B and A. So the dot product is commutative. The property 3 reads A dot the sum B plus C, which is equal to A dot B plus A dot C. This is called the distributive property of the dot product. So the dot product distributes over the sum. And the fourth property says the scalar multiple of A dot B equals to the C times the A dot B, or is equal to the A dot, the scalar multiple of B. It simply means that we can easily move the scalar C from anywhere to any other place. We can keep it with A, we can keep it out of A and B, or we can place it with B. The fifth property says the dot product of A with 0 vector is simply 0. Let's prove some of them. So we can consider A is a vector of a three-dimensional space with components A sub 1, A sub 2, and A sub 3. Then by definition, the dot product of A with itself is simply the sum of the squares of the components of A, which is simply by definition the square of the magnitude of A. This is the end of the proof of 1. Let's try to prove 2. It simply says the dot product is commutative. It can be proved easily as shown. So the dot product of the vectors A and B is by definition the sum of the products of the corresponding components of each vector. Since A sub 1 and B sub 1 are scalars, so is the product. So we can write the first term in this product as B sub 1 times A sub 1. And similarly, the next term, A sub 2 times B sub 2, can be written as B sub 2 times A sub 2, and so the third term. Now this is by definition the dot product of the vectors B and A. This clearly shows the dot product is commutative.